All right. A lot of stuff going on in this, and part of what we need to understand is what shape we are dealing with. Taking that, I draw the three-dimensional rectangular storage container as what's called a net layout, where we kind of just lay it flat and look at the different shapes, different sides that we are looking at. So a rectangular storage container with no top on it, which means we've got the bottom of this rectangular storage container, which I'm looking at right now, and then each of the sides laid flatly. Okay. And it does give us a little bit of information about the initial condition that we're looking at here. It says it has a volume of 10 meters cubed. And I know that in a rectangular prism, volume comes from length times width times height. It gives us a little bit more to deal with as well. It says the length, this equation right, or this sentence right here, the length of its base, which I have right now is identified as L. The length is twice the width, is equals twice the width. So L equals 2W. So kind of putting that information into here, as well as the 10 for the volume, I could rewrite this as 10 equals, replace L with what it equals, 2W, and W times W, good conversation for us to have right now, algebra, W times W is W squared, right? So as we're looking at this picture, kind of putting that in there, we are looking at a picture of the base right here, and this is the length and the width, except for they tell us that the length actually equals 2 times the width. So I can call that side 2W and the other side W, and that these little lengths on the side are H. Okay. And then we get into what we are trying to optimize. And up until this question, a lot of what we were optimizing was like the volume or the surface area. And this one, we are actually optimizing cost. And so in this, it says material for the base costs $10 per square meter. Material for the sides costs $6 per square meter. Find the cost of materials for the cheapest container. So as I talk optimization, am I finding a max or a min? A min, right? Cheapest would be the minimum cost. And the equation that I'm minimizing is very tricky for the first time we've seen something like this, because I have to go through and kind of talk about the cost of each of the sides, and they all cost a little bit different based off of the information given above. So start with that first sentence. The material for the base, which would be this rectangle right here, the material for the base is $10 per square meter. So per square meter would be times its area, right? So $10 times the area of the base would give me this first equation right here. 10 times, and the area of that rectangle would be 2W times W, or 2W squared. And this right here would be the base of our container. And then it starts talking about the other sides. This is his material for the sides, and we kind of have two different types of sides. If we were to like fold this up, I would call like that the front and the back, and the right and the left. Okay, is that okay if I refer to those as front and back, and right and left of our container? Okay, now those would all be considered sides, and they're $6 a square meter, but they're slightly different dimensions, whether you're talking front and back or left and right. So we kind of have to break those up per. So if we were to look at like the front and back, again, $6 per the square footage of that. There are two of them. There's a front and there's a back, both of which have the same dimensions, and that dimension would be 2W times H, times the height of our container, right? So I would have 2WH in there. Again, 2 because there's a front and a back. That's the dimensions of it, $6 per square meter. Yep, meter. Questions? Okay, so there's your front and back, and then with same idea for your left and right. is that it is $6 per square meter. You've got a left and a right, so there's two of these sides that have dimensions of W by H. Okay, do you see how that was a little bit trickier than maybe some we've talked about that are just straightforward like volume formulas or surface area formulas? But is everyone okay with what we've kind of talked through here so far? So cleaning this one up, it does clean up okay. First of all, 10 times 2, let's see, 20 W squared. 6 times 2 times 2 would be 24. And 6 times 2 is 12. These are like terms. Those are both WH's, so I can add those together and get 36 WH. And this is our cost formula, but it currently has two variables in it. So that's where I'm going to go back to my initial conditions and solve, so I can do a substitution into this and get it down to one variable. Okay. Again, we've talked about it doesn't really matter which one I solve for, but I see that there's only one place I would have to sub in H. So maybe I choose to solve for H over here, so I can just sub in that one spot. Okay, so if I were to solve this for H, this is all multiplication. I would have to divide by 2, and I would divide by W squared. 2 over 10 would be 5 over W squared. So I can now go over to my cost equation, replace H with 5 over W squared. And the last thing I would do before we finalize our cost equation is clean that up, because this I can actually clean up, right? If I look at it as a fraction times a fraction, multiply straight across the top, straight across the bottom, simplify, like, for example, we could simplify the fact that there's a W in the top and 2 of them in the bottom. So I could take out a W from the top and bottom there. Multiply those together. 36 times 5, 180. And we'd get down to this cost equation that we are trying to find a minimum of. It's the same cost equation we had up here, just cleaned up and down to one variable. Okay. So now we move into the calculus part. We haven't done any calculus yet. We've done algebra so far. Ugly. Questions? Okay. So let's talk about the calculus part of it. To find the maxes and mins of this function, I would run it through my first derivative test. So we're going to go to our derivative then. So our power rule here. And remember, we kind of think of that 180 over W as 180 times W to the negative 1 to help with doing our derivative, so that I can just do my power rule. It ends up being negative 180 W to the negative 2, which I could drop back to the bottom of that fraction. Because I know I'm looking for my critical points, I would not want to leave those separate. It is a lot easier to identify my critical points if I make that into one fraction, because my critical points then are the numerator zeros and the denominator set equal to 0. So to finish this out and get this to be one fraction, I would get a common denominator, and that would be multiplying top and bottom of this one by W squared. Questions? Okay, so critical points. This one is able to be 0, and it is able to be undefined. It's a fraction with both of those able to equal 0. So I would set my numerator equal to 0. I would set my denominator equal to 0. Solve each of those. Denominator is really easy to solve. Got a critical point at 0. Okay. Work on the numerator there. Add 180. Divide by 40. Cube root. And somebody give me that ugly number. need somebody to agree with that. Good? Okay. Before we start moving on. Okay. We did not have a conversation right now about the domain, so let's just talk about our domain real quick. Again, remember that your domain decision comes from what variable we ended up deciding to write this in. And we wrote ours in terms of the W, in terms of the width. So if I were to go back to my volume equation right here, 10 equals 2W squared times H, the smallest W would be 0, right? And the biggest W would be is if H was so tiny that it was essentially negligible, not there, and solve that equation, 10 equals 2W squared for W, which means I would divide by 2, 5, and square root. So the other, the largest W would be approaching the square root of 5, which is something ugly, 2 point, who's got that for me? 266, 226. 3, 6. Okay, questions on that part of it? So that gives me my number line to work with. 0 up to 2.236 with a 1.651 in the middle. I am testing this into my derivative, right? Because these are signs of my derivative to tell me about what my function is doing. Something between 0 and 1.651 would be like 1. If I come over to my derivative and plug in a 1, 40 times 1 cubed is 1. So that'd be 40 minus 180 would be negative, right? Over 1 is still negative. Plug in something bigger than 1.6, less than 2.2 would be like 2. So 2 cubed is 8. Times 40 would be 320. Minus 180 is positive, divided by a positive number is positive. So that tells me my function would have been decreasing and then increasing, making this a minimum of W, right? We just found the minimum of our width. Questions so far? Now, sometimes we kind of forget where we are headed with this and say, okay, I know the width is 1.651. I can find the length because the length is 2 times W, so just take that times 2, and there's my length. I can find the height, 5 divided by 1.651 squared. That gives me my height. There's my dimensions. Did I answer the question? No, the question was not what are the dimensions. That's how I would have found them had that been the question, right? But the question is, what's the cheapest this could be? So my cost, my answer is the cost. Guys, you have the cost in terms of W right here. All I have to do is go to my cost formula. I don't even have to find anything else out as far as length or height because cost is in terms of W here. Plug in 1.651. And I have no idea. Questions on that? Yeah.
Which equation do you use again to find the domain?
So I paid attention to what we wrote our optimization in terms of, and we picked width. So then I came back to my initial conditions, which was the volume formula, and I went to that and I looked at finding the biggest W could be. So basically making any other variable H 0 or non-existent. Other questions? Does anyone have an answer for me so I can finish this out? What'd you say?